All right, we're back. We're live, I believe so. Hello, welcome. So yeah, it took a few minutes. It took like a pretty good amount of time to kind of relax here. I wanted to lay down for a few minutes. I don't know. I'm just feeling very kind of tired. A lot to think about. Oh, very quickly, I wanted to just review something. Let me do that before we get into the next problem, just because I feel like guilty. Yeah, I really messed up before my logic on this problem. So what I wanted to say was, if you have a cycle of nodes, and yeah, I'll do it this way. The problem, so to like make it very succinct, you have in k iterations, you have A, and then you have some amount, we'll call it C. And you have some k iterations where you move A number of nodes and C nodes, and that's the slow pointer, right? That moves one at a time. And we know that only it doesn't make any loops inside the cycle because it moves too slow. The other one moves in the time that this moves one cycle. The other one moves, two. So at best, they could meet here, I guess. But you won't because we don't know where the fast pointer. So there's a fast pointer that moves twice as fast every one. The slow pointer makes one hop, and the fast pointer makes 2 hops at each iteration. We don't actually know where the fast pointer ends up being when it finally gets inside this loop. But actually, it's the other way around. It gets inside this loop way sooner because it's moving twice as fast. It's going to get inside the loop before the slow one does. We don't know where it is. It doesn't matter where it is. No matter where it is, it won't take more than one cycle. It won't even take a full cycle for the fast pointer to catch up to the slow pointer. Now, what's interesting about that, though, is that now in 2 times as many iterations, right? Because the number of nodes, so k is sort of is the number of nodes we hop for the slow pointer. For the same number of iterations, you actually have twice as many nodes for the fast pointer. So the fast pointer is twice as many nodes. It also moves A, right? So this node is going to be, this A plus C node is exactly the node where they meet, the slow pointer and the fast pointer meet. So this pointer is going to make it's going to go A, and it's going to make some number that we don't know of loops within the cycle. We'll call that B. Let's let this whole thing be B. Makes our unknown number of loops, which is non-zero. We know it's at least one loop because this faster pointer gets into the loop before the slower pointer, and then it has to actually catch up to the slower pointer. It needs to make at least one loop. So we know it makes at least one loop, and then obviously, from A, one loop, it also now makes that C gap, that C distance. So now we have this formula where we could say 2A plus C is equal to A plus alpha B plus C, where alpha is greater than or equal to 1. And then we can say A is going to be equal to alpha B minus C. And this, so we have 2A, we subtract A from both sides, and we subtract 2C from both sides. So we get A equals alpha B minus C. What's interesting about this is that means that you could actually rewrite this as A equals some alpha minus 1 times B plus B minus C. And the reason why I wanted to write this, I wanted to show this, is that what that means is this amount here it'd sort of be like this guy. This is exactly b minus c number of nodes. And if you took a minus b minus c, so here's a minus b minus c. And right, this is b minus c here. What that means is a minus b minus c, or a, it's really a minus b plus c, is equal to alpha minus 1 times b, where this could be 0, which is to say that this is equal to 0 mod b, which is to say that b divides a minus b minus c, which means that you can loop over b as many times as you need to, and this point, this node, like, so once you move, so if you take a pointer and you stick it at the beginning here, and you stick it at this meeting point, and you move those b minus c nodes to get to the beginning of the array, of the cycle rather, and you move over here the b minus c nodes, what it means is not only are you at the beginning of the cycle here, but if you wanted to progress the rest of the way, all that's going to happen is if you move both of these nodes simultaneously, right? This one makes a move, this one makes a move, just one move. Then they're both going to meet at the entry point of the cycle, because the one that's already there is going to loop over b alpha minus 1 times, and this portion here is the rest of the way, and they're equal. This is actually broken into, you could say this is sort of b plus b plus b, right? 0 or more sections of b. So that's really neat. So that's something I wanted to kind of like quickly look over again, like really explain this a little bit better, because I not only did I not explain it very well just before, but I don't think I really understood it myself. Like, I think I didn't really get it. It's a very nifty thing, but this is basically the math to kind of show why this works, why you can basically have your 2 pointers meet in the cycle and then take 1 pointer, stick it in the beginning, and then just keep cycling these pointers, keep iterating these pointers until they meet, and that should be the beginning of your cycle, because the one that's in the cycle will just keep cycling, and the one that's outside the cycle will move exactly a certain number of cycles away until it actually hits the beginning of the cycle, and the difference between sort of, there's this extra piece before you actually hit the beginning of the cycle, is exactly this b minus c, and we know there's at least one portion of this b minus c where this math works out. So it's pretty wild. It's pretty interesting. Like, it's very that I think is the right way to explain it. Like, it's hard. It has been hard for me to understand it, hard for me to explain it. But I think that's the way to explain it, is that you can understand this by breaking up into 3 different pieces: is the size of the cycle, where you end up in the cycle when they meet, and the beginning portion before you get into the cycle. And then you can kind of do the math to realize that there's this relationship between the meeting point and how many nodes you need to go until you reach the beginning of the cycle, and then there's a certain number of cycles that you actually can traverse, and that number, if you add all of those cycles that you did and that extra portion to get up to back to the beginning of the cycle, if you add that together, that actually for some number of cycles is actually equal to the number of nodes that it took to start before you got into the cycle in the first place. And all you've got to do is just set 2 iterators at the intersection point and at the beginning of the whole list, and just run them, and eventually they're going to meet, and they're going to meet at exactly the beginning of the cycle. Really, really interesting, really amazing. But yeah, not something that I would have come up with on my own at all. Like, absolutely no way would I have come up with that on my own. That's so much more like clever than anything I would have ever thought of. But obviously, I saw that somewhere else. But it's like, it's every time I think about it, it's hard for me to explain it. I don't even know how you would come up with that on your own. Like, it's really amazing. But the idea is that you have this cyclic kind of relationship here. Really, I think this expression is really the best way to understand it. I think right here, where you know that this entry into the cycle, the number of nodes you need required to get into the cycle, is equal to some number of cycles plus the difference between the size of the cycle and wherever that entry point is. So you can just move that pointer back up, and then you can actually keep moving those pointers in tandem, one just moving through the cycle and then the other one just moving until they meet. And it's amazing, and it's just nothing short of amazing. Yeah, you don't even need to know what B is for this to work, which is also really amazing. So that, I think that's the thing that really gets me, is that there's this kind of like these sort of implicit calculations going on here, that you never even need to know what B is to figure out what A is. And then obviously once you know what A is, then actually you can figure out all the other numbers too if you wanted to. You could technically figure out what. Can you figure out what K? You could count. Yeah, you can count the number of iterations that it took to get for the nodes to meet. So that can give you K, and then you can find A. You could subtract K from A to give you C, and then you could subtract A and C from 2K to give you alpha B, and then, well, I guess actually once you found the beginning of the cycle, you can just loop once from there to figure. Also, if you know how many nodes there are, well, I guess you don't know how many nodes there are. I guess that's the point, is you're trying to figure out how many nodes there are. Yeah, what you'd want to do is probably just loop once from there to figure out what B is, and then you have A and you have B, and then you can you probably would want, yeah, that can give you the total number of nodes in the. I mean, you kind of know everything after that, right? Once you know the beginning portion, and then how big the cycle is, how many nodes are in the cycle, you should be in good shape. I think. Yeah, you can count all these things too as you go. You can count K. You can count K. You can count A. You can count B. You can get all these values. Pretty interesting question. Pretty interesting question. All right. Anyway, let me move on. So that actually isn't the problem that we were supposed to look at now. But I kind of wanted to clear my conscience, because I was talking about this earlier, and I was like, man, I really didn't explain that well. I really didn't do it justice. And the reason why I'm going over it again is because, like, obviously I didn't do it justice because I didn't remember it. You know, when I looked at this problem so many times, and it should be like this now. Like, I should just immediately know the answer because I've done it so many times over the years. And we're talking like 5 or 6 years ago I looked at that problem, and I'm still like didn't really fully understand it. So that's pretty wild. But anyway, let's continue. So this is the actual problem we want to do now, or the one we're prompted to do here. Unique word abbreviation. The abbreviation of a word is a concatenation. Oh, well, that's a lot of downvotes. Concatenation of its first letter, the number of characters between the first and last letter, and its last letter. If a word has only 2 characters, then it is an abbreviation of itself. Dog is a DLG. D1G. one letter between the first letter D and the last letter G. Internationalization is I18N, because there are 18 letters between the first letter and the last letter N. It is it, because any word with only 2 characters is an abbreviation of itself. Implement the valid word abbreviation class. Valid word abbreviation initializes the object with a dictionary of words. Boolean is unique returns true if either of the following conditions are met, otherwise it returns false. There is no word in dictionary whose abbreviation is equal to words abbreviation. For any word in dictionary whose abbreviation is equal to words abbreviation, that word and word are the same. Oh, okay. Example, valid word abbreviation is unique, is unique, is unique, is unique. Dear door, cake card, dear cart, Kate. Dear door, cake card, dear cart, cane, make. Null, false, true, false, true. False, true, false, true. So, I mean, a couple things here. Don't actually need to do this at the top, but I just think it's a good habit. Interesting. You know, to view this question, you must subscribe to premium. Oh well. I'm sorry. Yeah, this is a premium question. I mean, hopefully it makes sense. Hopefully you can kind of follow along either way. Either way, yeah, I have a premium account. I've had a premium account, I think, for, I want to say it's been like 3 years now that I've had it. Over 3 years. I like it. I like the site. I support it. Length of dictionary is small. Dictionary of I.length is less than 20. Dictionary of I consists of lowercase English characters. Word length is between 1 and 20. Word consists of letters. 5,000 calls we made to is unique. I don't think I fully understand this question. Like we just need to have this is unique function. Is that it? I think I get it with the abbreviations. Initializes the object with a dictionary of words. Returns true if either of the following conditions are met, otherwise returns false. There is no word in the dictionary whose abbreviation is equal to words abbreviation. Okay, so one of the first things we want to do is probably take the dictionary and convert all the words to their quote-unquote abbreviations. I wrote a routine to do that, and then just put all those abbreviations into, I guess, into a, we'll probably write a subroutine that's like just an abbreviate subroutine, and we'll call it use that, make use of that between these calls, and then just put that abbreviation into a set, I guess. It might be either a set or a hash map, one or the other, but a hash set or a hash map. I think I can do that with strings. So there's no word in the dictionary whose abbreviation is equal to the word's abbreviation. Okay, that's interesting. So that's just a simple check with within the hash map. Either of them are true. Okay. So if that one's true, return true. And then if for any word in dictionary whose abbreviation is equal to word's abbreviation, that word and word are the same. So if there's no oh, that's interesting. Okay, so this is sort of like a slightly compressed way of checking whether or not the words are in the dictionary by using abbreviations of the words. So then if the word is in the dictionary, then we want to, or if the abbreviation is in the dictionary, then we want to check the words directly. Okay, well, yeah, I mean, you could just use a hash map of the string to its abbreviation. That's probably the simplest way to do it. I'll do it that way. said welcome back, but welcome back. And then we'll have a subroutine here. We'll just be abbreviate. Say if what is the abbreviation for words that only have one letter? Can we do 2 use cases? Can I do this? We need to store the abbreviation as a string. It's just 2 characters and an int. No need to put that together again. Yeah, but then you need then you have to store it in a special way, right? Because I mean that's fair. I mean a string is not really necessary. Although you would need like 2 characters and a string. Like I don't know. Can you use a tuple as a map, an integer? 2 characters and integer. I agree with you, but it's kind of like we could actually try that. We could try that in a second. Let me see. Let's see if we can do that. That's a good call. Let me think about that. I like that. I like that. We'll use tuples. I'll try to use tuples. A couple things I want to check. If I can use tuples in a hash map. I don't know if I can. I don't think the STL has a hash for tuples. Maybe it does. I don't know. We'll see. Let me see. Like a built-in hash. Let's do a, and let's do like a here. Pretty sure I've checked it before. Because if I have to, the other I mean I could use a regular map. That would have a tuple, have support for like hashing tuples, basically. True. Okay, that's interesting. So not only does A work, but A should be true. Interesting. So I think single characters should be supported as well. Yeah, interesting. So okay, yeah, we'll do single character. That should be fine. I think we do single characters. But now I'm curious about can I do this? Let's try this. Let's do 2 characters and a character, and int. Let's give that a shot. Does that exist? Yeah, I thought maybe it doesn't. Right, let's just make sure that's the cause of the compiler. I could probably read the error and find out, but let's just do it this way. Just a little faster. Yeah, I'm pretty sure it's not supported now. What's interesting though is a map. A regular map, I'm pretty sure would work. See, the thing is, I'm not sure if it's better to use. Yeah, so that does compile. That's the thing with C++. Python, I believe you can hash tuples, more or less. You can still use tuples in a dictionary, but C++, you can use a regular map, but an unordered map, you basically need to have like a hash function for your tuple. It doesn't really have that built in, which is really annoying. I don't like that. It bothers me. But I think you'll need a custom hash function. Right, exactly. Which I don't even know I don't even know what I would do for a custom hash function. You know, like I don't even know what I would do. I don't want to write a custom hash function. I don't like hash functions. They make me uncomfortable. They're weird. You know, they're kind of weird. Like writing an efficient hash function, hashing scheme is like, I don't like doing that. I don't like doing that. Yeah, exactly what you said. I think you'd have to write your own hash. So we'll just use, we could have our choice between unordered map with a string or a map with a tuple. Technically a little bit less efficient if we do it this way. I think we'll just do it this way. That's fine. I agree with you. I think it's overkill to store it as a string. Oop, I did that wrong. I think it's overkill. We'll do this with just a regular map then. So what we want to do is just edge cases. S is empty, or s.size is 0. Then we're going to return make a tuple with no character and no integer, right? Empty, null. Can I do like a null character? Is that a thing? Like just a 0, just a flat out 0. Not sure if I can do it that way. The size is 1. Return, I wonder if this will work. That character, and then also 0. And then finally, one more time. Yeah, you know, you can do something like this. It's going to be s of 0, s of s dot size minus 1, and then the difference between the size, really just the size minus 2, right? It would be the number of characters, which you can get by the size. Yeah, I guess I do it that way. Yeah, I guess it's fine. That should be fine. And sure. I think this will be okay if we do it this way. Yeah. So now we can say for S in dictionary, we're going to take our map of do we want to, I don't know if I should do it that way. And we're going to say abbreviate of S. And now we say is unique. We have 2 conditions. There is no word, so bool, say C1 or just B1. Abbreviation equal to abbreviation, so abbreviation map dot count is greater than 0 of no word whose abbreviation is equal to this word's abbreviation. So we can abbreviate this word, this rod, abbreviate this word, and then if B1, we'll say any word whose abbreviation is equal to words, that word and word are the same. Any word in dictionary. Oh, so there could be multiple words, by the way. Actually, this could be. This actually could be something like this. It's actually more appropriate. Yeah, I didn't really think about that. And then any word in the dictionary whose abbreviation is equal to this word's abbreviation, so the same key, that word and word are the same. Okay. Say initially true. Say for auto S in the dictionary or the abbreviation map of abbreviate word I don't want to call that too many times. I wonder if that works. I don't know if I could do it this way with a reference. You could try it. Side note, Boost has a facility to combine hashes. Oh, neat. Keep that in mind. Yeah, I don't know much about like custom hashing. I don't really do that much. Depending on how clean you want to make this, I like that you add all the headers, all those standard headers can be assumed included. True. You can easily encode all bits of the abbreviation into an int. Oh yeah, you're right. Well, not necessarily, right? Well, probably. I mean, probably, right? Because, well, you could do a long. How big are the words? Oh, the words are very small. Oh, you're right. Yeah, you could. That's true. You could use the first 2 bytes. Should be plenty, and then obviously each character is 1 byte. So you could just map the mask for the first 2 bytes. Oh, that's fair. I didn't think about that. And wait, no. Yeah. Because actually, you can even do right. You can even do 4 characters, right? You can even do that because this could be 0, 1, and 2, 0, right? You only need two digits to represent the word. So you could do it that way too. Let me think about that. Yeah. I want to do that. I would rather do that. I like that. That's kind of neat. I like that. That's extra credit. And that shouldn't be too much harder to do. So we say, let's do it this way. We'll do character A, character B, and we say int is always going to be x is going to be s.size minus 2. Okay, so there's no characters, so we just return 0. Size is 0, return 0. Size is 1, then we want to say just the first character, which is going to be it's times 3 bytes, right? So we would do A, or character X, let's call it X, or yeah, we'll call it X. X is going to be S of 0, right, and that's going to be the first byte, and we want to basically mask that first byte over all the way towards the left side. Now, should these be unsigned integers? I think so, right? Unsigned integer, no. Let's not do that. Because these could be zeros or ones, right? Unsigned, actually, we can't modify that, the signed bit. So we actually want to take this character and bit shift it to, it's really going to be this, right? Bit shifted to the left 24 bits, right? Something like that. And then everything else is 0. And then here we say, we're going to do it like this. We're going to say character A equals S of 0, B equals S of size minus 1. And we're going to take X equals this size. We're going to say character C is going to be we could do D equals X modulo 10. Plus 0, that character, and X divide equals 10. And C, A, B, C, D, C would be then X modulo 10 again, plus this, make it a character. Yeah, make these characters. And then we want to add them together, mask them together. It's going to be sort of or, right? It's going to be A bit shifted to the left 24 times, ORed with B bit shifted to the left 16 times, and C bit shifted to the left 8 times, and then D. Something like this, right? That should give us our integer. Hopefully, I don't know. Maybe I should have tested to see. Let's see. How clean you want? I like the arrow letter. Easily encode all bits into an int. Help for review. Let's show it. Abbreviation, const string, u, unsigned in 32. Oh yeah. Static unsigned character front or static cast unsigned character back, character bit, size, character bit. Oh, interesting. Plus some asserts and static asserts added in real life code. Make sure all assumptions are held. Oh, right. Yeah, I guess that's true. Well, actually, if you just make them all ints, I guess one issue with ints is that you need some assertions to make sure that it's like, I think you would do like int 32, right? I think that's. Let me see if we can do that. Hold on. Int 32t. That's really what we want. I think you're fine with int 32t. Fastest unsigned. Interesting. Yeah, I think we just do int 32t. I think that works. I believe so. Let's make sure we have enough space and character. I mean, the character's always got to have at least 8 bits, right? Can we do that? Character with 8 bits? Or should we just do 8t? Do int 8t, I think, right? I think that'll work. We do int 8t. I hope so. Just to try to make these guarantees. Character bit is guaranteed to be greater than or equal to 8. Oh, interesting. Excuse me. Oh yeah, you did character bit here, right? Right. Oh, you put the size on the way on the left side. I put the size on the. I actually encoded the size into 2 characters and used that. I don't know if that's better. I don't know, because the size is. Oh, the size is kind of small, right? The size really could just be 3 characters if you really wanted it to. Yeah, actually, you don't even need to do. Yeah, the size is so small. The size is literally 3 bits. I think. And you get the size. It's not even 8 bits. All right, I take it back. Yeah, so actually, you don't even need to do this. It's not even necessary. So what'd you do? You said C, and you said 8. You said, what do you want with? You went with character bit. Yeah. Let's say const expression uint, yeah, or just int. Something like that. Yeah, something like that. Let me see what you had here. Compare mine to yours. Yeah, if we're just return 0, if the size is 0, if the size is 1, then these other two pieces are 0. Yeah. Okay. What do we have? Static cast s dot front is unsigned character, or static cast unsigned character back, front, back, and finally the size. Yeah, and I guess the abbreviations don't even matter to the mapping, because you don't need to subtract by 2, or subtract 2. You really don't even need to do that either, because just thinking, if you have an empty, I think the one problem you'll run into is they said they won't have. I don't know if they said they won't have words of only two. Yeah, the word length could actually be 1. So you do run into a bit of a problem, right? Because the word length could be 1, in which case I think you run into an issue. Because you have your. Oh, no, I'm sorry. No, you're fine. Never mind. Doesn't even matter. Actually, what you just did doesn't matter because. Sorry, it doesn't matter. I'm trying to look for problems because. Also, what do they call that? The word length being 1 means the front and the back are always. I like what you did, actually. I'm going to do what you did. You don't need these edge cases. Given the constraints, right? Given the constraints, you can just do. Yeah. Here. Front. Back. And then size. You're saying use static asserts. Do you need to do that? Or can I just do these directly? kind of want to try this, see what this looks like. I guess for legibility, I'll do sort of A, B, and C. Or just A and B. Hey, I like what you did. You do a kind of a version of it. Okay. Now back to the question. Pushback S, abbreviate S, pushback S, right? Now we're saying if you have Boolean 1, if Boolean 1, so really you could just do this. The abbreviation doesn't really need to be referenced anymore, does it? Now you just want to say Boolean check, assume it's true, and you say for each string in our vector, we want to say, what does it say? Any word in the dictionary whose abbreviation is equal to this word's abbreviation, that word and word are the same. So they need to be the same word. So this word equals, check, word equals, all right, every word in S. It's a little confusing, but and otherwise return false. So really, both of these have to be, that's really confusing. They've got to both be true, no? Oh, is this not, am I crazy? Wait a minute, if true if either of the conditions are true. Whoa, what? I have to really think about this now, actually. That's a little weird. For me, the two characters are fixed with under all circumstances. The size is the only thing that could be variable size, even though it is clamped by the problem description. Oh wait, no, there is a small problem. I'm sorry. I was thinking with this one character, then this could match single character strings to two character strings. So actually, this could be wrong. Could be wrong. And this obviously the size doesn't matter. I'm just thinking. What's that noise? Something with some banging. Actually, how do we differentiate the... I think I do want to handle these different cases, because you could run into issues where like AA and A, those two abbreviations. Not really though. I mean, you couldn't actually. No, I take it back. I don't know if this it shouldn't matter. It shouldn't matter, right? Because if you have the single character case, the size is 0 at all times. You're never going to match that against anything else. Or size is 1 at all times. That won't match against anything else. Yeah, I take it back. No, we're fine. We're fine. Gotta think about it a little bit though. Two characters are fixed with under all circumstances. The size is the only thing that could be variable size, even though it is clamped by the problem description. Right, right. Putting it in front, should it ever change, all I'd need to do would be choose a larger integer type and leave the algorithm as is. Oh, I think I see what you're saying. I think I understand. Should you ever need, what was the... Actually, I'm not sure what you mean, but what you mean by putting, I guess, it in front means maybe A. But anyway, they're actually, I think we're okay with the abbreviate encoding. But the thing that's not okay is this. Maybe this is why I got so many downvotes, is because this doesn't make sense. If you really think about this carefully, returns true if either of the following conditions are met, otherwise false. There is no word in dictionary. There is no word in dictionary whose abbreviation. Oh, excuse me. I'm sorry. If abbreviation map.count of abbreviation is 0, that's not, then return true. Ah, that's the first condition. Now, the other condition is here. Gotcha. Now we know that there's something in there for any word whose abbreviation is equal to this word's abbreviation. That word and word are the same. Yeah, actually, you really, well, okay, that's fine. So we'll just do it directly. So for every string in this mapping with that abbreviation, I don't know why I'm having a hard time, but for some reason I'm looking at this, doesn't look right. We're gonna and check that this word is equal to the string, and then return check. That should be enough. How do we do? What? Oh. I don't actually know where I put that. I guess you could make that like a private static member, maybe? I don't know. Unexpected unqualified int. Oh. Oh, no kidding. Oh, that always exists. I know that. Oh. Oh, we're in good shape. Should we just go for it? I'm tempted to just go for it. We spent a pretty good amount of time on this. Do we just go for it? I'm so tempted. Yeah, I'm gonna go for it. Probably got something wrong. Oh, we got it. And we're wicked fast. Look at that. Less memory than most people, and 100% faster than everybody else's solutions. Sweet. Yeah, that's because of the encoding. That was a really clever way to encode it, by the way. Just, you know, very clever, very clever. Although we are making a lot of assumptions about. I mean, they gave us the assumptions that we're working off of. We did make a lot of assumptions here. Sweet. All right. Well, thank you guys. Thank everybody for coming by and saying hello, watching for this this problem. I'm going to end the stream and start another routine, or another, what do they call that? Another problem. Stream again, another problem. This is cool. I like this. This is good. I don't know why it's got so many downvotes. People didn't like it. I thought it was interesting. This is definitely an interesting. Yeah, definitely interesting. I'll just say interesting. So nice. Yeah. Hey. Yeah. Not bad. Not bad. All right. Okay. Let's go. Let's do that. So let me full screen for a moment, and I'll be right back.